Growing up, I was always captivated by the wonders of classical physics. I remember being fascinated by the laws of motion, gravity, and the elegance of planets circling in our solar system. But as I delved deeper, I began to realize that there was an entire universe beyond what can be observed with the naked eye. This universe, where Newton's laws of motion stop working, where particles behave like ghosts until you look at them, where objects separated by light years, acting like they're connected by invisible string. This universe is called quantum physics. My name is Masha, and I'm going to be your guide right into the quantum realm. This is episode 1, and today we'll be chasing the quantum waves.
But what exactly is quantum physics?
Quantum physics is a branch of science that deals with the study of matter and energy on the microscopic level, like atoms and subatomic particles. Unlike the world we see around us, which is referred to as classical physics, those particles don't behave in a way we'd expect. Instead, they follow their own set of rules, which often seems bizarre and unpredictable. This is also the reason why quantum physics is widely considered to be one of the most challenging and complex scientific branches.
In fact, Richard Feynman, the famous theoretical physicist, best known for his remarkable lectures on the topic, stated, "If you think you understand quantum physics, you don't understand quantum physics." Which, in reality, is an extremely misleading quote, since we do understand quantum physics really well, to the point where we're able to use this understanding in the practical sense, creating technologies like MRI scanners, lasers, solar cells, electron microscopes, atomic clock, and many more.
What Feynman actually meant in this quote is that quantum physics is extremely non intuitive, or even counterintuitive.
So, any classical analogies you may come up with to try to account for its effect or describe the particle's behavior are probably wrong, or at least incomplete, since it describes a microscopic world with rules that are fundamentally different from the macroscopic world we experience every day, challenging our intuition about reality and making it impossible to form correct predictions purely based on the logic from our world without knowing in advance what exactly you should expect.
This counterintuitiveness can best be seen in one of the centric ideas in quantum physics wave particle duality. As you may already have heard, the light can act as both a particle and a wave. It can be reflected off surfaces and bend as it passes through a medium, like a wave, while still keeping its energy quantized, meaning it exists in limited amounts rather than a continuous range. In the quantum world, everything has a wave nature. Light, particles, and even macroscopic objects from our day to day life. One of the most famous experiments that illustrates this phenomenon is the double slit experiment, originally performed by the British scholar Thomas Young in 1901 in order to prove the duality of light, and later rediscovered by other scientists like Davidson and Gamer in 1927 and Klaus Johnson in 1961. In this experiment, we have a wall with two parallel slits in the middle, through which light beams are passing through, and we are observing the pattern that forms on the further wall. Which doesn't sound like an exciting experiment, does it? Since it sounds pretty simple. There are two holes, so there should be two strips of light on the other end as a result, right? Wrong. In reality, as light particles are passing through both of the slits simultaneously, they exhibit a pattern that forms multiple vertical lines that brighten up as they are closer to the middle, gradually fading as they are spread out along the surface. So there are light and dark lines throughout the wall. This phenomenon is referred to as the interference pattern. This happens exactly due to the wave nature of light. Photons pass through both slits simultaneously, and the light going through each slit interferes with one another. Though the peak of the light waves amplitude line up together, forming the light lines, and their amplitudes cancel each other out, forming a dark line. But where it gets really fascinating is if we place a detector at one of the slits to observe which slits the photons goes through, the interference pattern seems to just disappear. Instead of behaving like a wave, the photons act like particles going through one slit or the other, forming two parallel strains of light as originally expected. The act of measurement forces us to choose one slit and behave like a particle. This happens because in microworld, an observation requires an interaction, which disturbs its original state. This quick change from the wave into particle is called the collapse of the wave function. The most popular analogy for this would be if you try to take a picture of a bowling ball, but as you press the camera button, a thousand identical bowling balls come out hitting the original ball all at once. To observe a subatomic particle, it needs to interact with the particle of the same size in order to be detected, making it lose its superposition and settling on a singular path. Another reason why scientists love to call subatomic particles waves is because of a thing called the wave function. Wave function is the mathematical representation of the quantum state of a particle, like its position, momentum, and spin. Due to this concept being highly related to math, it would be way easier to explain it with the use of mathematical terms. So, as you probably already know, function is a mathematical expression defining the relationship between two variables. It basically takes in a value and spits out a related value. An example of such function will be a simple line like y equals x that represents a line, or y equals x squared that represents a parabola. Many of these functions are used to describe and calculate real life phenomenon, like when you throw a ball into the air. The path of the said ball would travel will form the shape of an upside down parabola. So, similarly, the wave function describes the behavior of the quantum particles and can be represented on the graph. For example, imagine a simple graphic for a math class with the x-axis and the y-axis on the other part. Unlike the line of the parabola, the wave function doesn't simply trace the path that the particle took. Instead, it showcases the particle's position in space that is given by the x-axis and the probability of finding this particle given by the y-axis. So, in our words, the higher the amplitude of the wave, the more likely you are to find the particle at this exact location.
So, technically, you can never know for sure the exact location of any particle, and instead you have to deal with limitless possibilities and probabilities.
The more understandable example of this would be the scenario where the police are searching for a jewel thief that just broke out of prison, but they can't pinpoint her exact location. Based on her known habits and recent activity, they can create a probability distribution map of which houses and neighborhoods the thief is most likely to strike next. This probability can be thought of as the wave probability, where the richer the neighborhood, the higher are the chances of a police to find the thief there, and the poorer the houses, the lower.
And if the police would be successful at finding the jewel thief at one of the locations, the distribution probability immediately collapses into a single point in space, with zero probability of finding it at any other location.
Just like I mentioned before, if we're able to measure the electron it takes a single location and starts behaving like a particle,
But this is also where our analogy fails, since in the real life scenario, the thief hasn't actually spread out across town, but instead was in a fixed location the entire time. and the only reason why she hasn't been caught was the lack of information.
While with the electrons and photons, on the other hand, then we don't know its exact position. We can't assume that it's a some defined place. It's not because of our lack of information that we can't determine its location, but rather a fundamental property of quantum objects. Quantum physics is a brilliant and unique world that still has a wide range for discovery inside of it, since the whole concept only began to exist 100 years ago. Even though we're still not certain about the majority of parts of the quantum world, it is a worth a journey to take, since similarly to any other subject taught in school, it explains how the world around us works and shows the very best of what humanity is capable of discovering and conquering to our own advantage. I hope I was able to spark at least a single spark of curiosity within you and make you stay along for the ride right into the quantum realm.